There are three things in the known universe that travel between stars: radiation, cosmic dust, and apparently whatever 3i Atlas actually is. Because on October 21st, 2025, alleged leaked footage from a Japanese space agency showed this so-called comet looking less like a dirty snowball and more like a spacecraft with running lights. Now, the legitimacy of this new footage is highly questionable and has not been verified, but it certainly raises questions as to what this object could really be. Dr. Avi Loeb noticed its trajectory enables a solar Oberth maneuver, the kind of gravitational slingshot an advanced probe would use to accelerate efficiently. Then amateur astronomer Tiago, also known as Dobsonian Power, captured it independently, same coordinates, same shield-bright front, no cometary tail. Now it's diving toward the Sun during the 1 week Earth's telescopes go blind from solar glare. Convenient timing for a natural object. Perfect timing for something else. Stay until the end to understand why the next few days might answer the oldest question humanity has ever asked. If these mysteries have your mind racing like they have mine, don't just stay in the shadows, hit like and subscribe right now, so you stay on the front lines as this story unfolds in real time. Drop a comment with where you're watching from, what time it is there, and whether you think the world is seeing the full truth behind these earth-shaking discoveries. And if you want to amplify this hunt for hidden stories, share this video on X, Facebook, Reddit, or even in your private chats. Thank you for standing with us. You are the reason we chase stories no one else dares to follow. Part 1. The Japanese Leak. What the new image allegedly shows. On October 21st, 2025, something appeared on the internet that should not exist. The image showed an object near the Sun that looked nothing like a comet. It looked engineered. You're staring at a clip that's been circulating through forums and social media channels for hours now. The quality is grainy, compressed, filtered through who knows how many hands before it reached your screen. But what it shows is unmistakable. There's an elongated form, metallic in appearance, hanging in the blackness near our star. Along its spine run bright nodes, evenly spaced, glowing with a white-blue intensity that makes your pattern recognition circuits scream artificial. There's no fuzzy halo around this thing, no diffuse cloud of gas and dust trailing behind it like every comet you've ever seen in a textbook. Just this sleek, symmetrical spindle suspended in space. The object in question is 3i Atlas, the third known interstellar visitor to breach our solar system. It was discovered on July 1st, 2025 by the Atlas Survey, a network of telescopes designed to catch asteroids before they surprise us. For 3 months, astronomers tracked it as it fell sunward, analysing its light, measuring its trajectory, cataloguing its chemistry. Everything pointed to Comet. Unusual chemistry, sure, but still a comet. A frozen wanderer from another star system passing through ours on a one-way ticket to nowhere. Then this image leaked. And suddenly, all bets are off. Look closely at what people are pointing out. The highlights along the body don't look random, they look placed, deliberate, like portholes on a submarine, or radiator panels on a spacecraft, or emitter arrays on something we don't have a name for yet. The glow is uniform, wrapping the object in a consistent luminous sheath that reads more powered system than ice ball reflecting sunlight. The symmetry is wrong for nature. Nature loves chaos. Nature makes potato-shaped rocks and lumpy snowballs. Nature does not make precision machine cylinders with evenly distributed light sources. The timing of this leak is critical. 3i Atlas is days away from perihelion, its closest approach to the Sun, scheduled for around October 30th, 2025. It will pass within roughly 1.4 astronomical units of our star. That's about 130 million miles, well outside Earth's orbit, no threat to us whatsoever. But here's the thing. For about a week surrounding that closest approach, the comet will be nearly impossible to observe from Earth. Solar conjunction. The Sun will be directly between us and the object, flooding our telescopes with blinding light, making any detailed imaging essentially impossible. It's the perfect blackout window. If you were going to do something near the Sun and didn't want Earth-based telescopes watching, this is when you'd do it. The geometry hands you a natural curtain. The glare protects you, and that's exactly what makes this alleged leak so explosive. It surfaces right before the object vanishes behind the veil, showing us something that contradicts everything we think we know, then disappears before we can verify it. Now let me be crystal clear about something. We are not claiming this image is authentic. We're treating it as an artifact, a catalyst, a thing that exists in the information ecosystem and has triggered a cascade of questions regardless of its provenance. The official scientific understanding remains that 3I Atlas is a natural object on a hyperbolic, interstellar trajectory. It came from somewhere beyond our solar system, it's making a close pass by the Sun, and it will leave, never to return. The idea that it could be anything other than a comet would be world-shaking, civilization-altering, the kind of discovery that redefines what it means to be human in this universe. But if this image is real, that's exactly what we're looking at. The circumstances surrounding the observation make verification nearly impossible right now. The object is approaching the Sun from a geometry that places it at low apparent elongation from Earth's perspective. That means it's close to the Sun in the sky. Observing something that close to a blinding light source is technically challenging even for professional observatories. Solar glare washes out faint objects. Atmospheric seeing degrades near the horizon where the Sun sits. Heat shimmer from the ground distorts the view. It's the worst possible conditions for getting a clean, high-resolution image, which is, of course, exactly the right conditions for a leak narrative to thrive. When verification is hard, speculation runs wild. So where did this clip actually come from? That's what we need to figure out next. There's a watermark in the corner, UFO 5537. Anonymous posts claim it originated from a Japanese space agency or observatory. But there's no official statement, no press release, no matching data in public archives. Just this clip floating in the digital void, stamped with a code that means nothing to anyone outside whatever circle created it. And then there's another question altogether, one that ties the image to something even stranger. If this were a craft, if some intelligence from beyond our solar system sent a probe into our neighborhood, what would it be doing near the Sun? Why risk the heat, the radiation, the sheer violence of that environment? Unless it's using the Sun for something, unless it's preparing to execute a maneuver that human engineers have known about for decades but never built the technology to fully exploit. A solar Oberth maneuver, the biggest gravity assist in the solar system, the ultimate slingshot. We'll get to that. But first, we need to trace this image back to its source, or as close as we can get. We need to understand who's claiming what, why, the provenance matters, and what's missing from this picture that would let us call it real. Because right now we're holding a photograph that could rewrite history, and we don't even know if it's genuine. 3I Atlas is out there, closing in on the Sun. The blackout window is opening, and somewhere in the noise between verified science and unverified claims, the truth is waiting. Part 2. Provenance and Credibility. Check of the leak. The clip started showing up on X around mid-morning Eastern Time on October 21st, 2025. Users with varying degrees of credibility began sharing it, each adding their own layer of commentary, speculation, and alarm. The common thread in these posts was the claim that the footage originated from a Japanese source. Some said JAXA, Japan's space agency. Others mentioned university observatories or solar monitoring networks. But here's the problem. When you go looking for an official statement from any of these institutions, you find nothing. No press release, no data embargo announcement, no instrument logs matching the timestamp or field of view, just silence. The watermark is the only consistent identifier. UFO 5537. It sits in the lower corner of every frame, a digital signature that tells us nothing about the actual origin. Watermarks can be added to anything by anyone. They don't authenticate content, they just mark it. And in this case, the marking feels deliberately cryptic, like it's designed to invoke mystery rather than provide accountability. If you were leaking classified data, would you stamp it with a code that screams unidentified flying object? Or would you strip metadata, anonymize the source, and distribute it through secure channels? The watermark feels performative. That doesn't mean the footage is fake, but it does mean we should be cautious. What's missing is everything that would let us verify this independently. Real astronomical data comes with headers. FITS files contain observation metadata, instrument name, exposure time, filter selection, pointing coordinates, timestamp with nanosecond precision, detector temperature, gain settings. If you hand an astronomer a raw frame from a professional observatory, they can trace it back to the exact telescope, the exact night, the exact sequence of observations. They can check whether the star field matches the claimed coordinates. They can compare the point spread function of stars in the frame to the known optical characteristics of that instrument. They can even verify whether the weather conditions and seeing quality that night would have allowed such an observation. None of that exists here. We have a processed clip, compressed, filtered, stripped of all the forensic details that would anchor it in reality, which means we're left guessing. So why Japan specifically? There are a few plausible candidates if you're looking for high-resolution solar or near-solar imaging capability in that region. Japan operates several national observatories with advanced solar telescopes. Institutions like the National Astronomical Observatory of Japan have instruments capable of high-cadence solar monitoring. University networks across the country maintain smaller research-grade telescopes. JAXA itself runs solar missions and maintains ground-based support infrastructure. Any of these could, in theory, have pointed at the right coordinates at the right time and captured something unusual, but none of them have come forward to claim it. And that's strange. If you're an institution with a world-first detection of something this significant, you don't stay silent. You publish. You hold a press conference. You coordinate with other observatories for confirmation. You don't let your data leak anonymously with a conspiracy-coded watermark. The alternative explanation is that this isn't institutional data at all. It could be from a private observatory, an amateur network, or even a foreign intelligence asset conducting independent monitoring. The problem with those scenarios is that they're harder to trace and even harder to verify. Private data doesn't have the same accountability structures. You can't FOA request information from someone's backyard telescope. And if the source is genuinely sensitive, if there's a reason they can't come forward, then we're stuck in limbo. We have evidence we can't authenticate. Then there's the question of whether the image itself is artificially generated. People have been poring over the frames, looking for telltale signs of AI manipulation. Some point to the smooth gradients, the almost too perfect bokeh, the edges that look suspiciously clean for something imaged through Earth's atmosphere. AI-generated imagery has gotten frighteningly good in the past few years. Tools can fabricate convincing astronomical scenes, complete with realistic noise, star fields, and optical artifacts. If you wanted to hoax this, you could. But here's the counter-argument. Harsh solar-adjacent imaging through filters and heavy processing can also look artificial. Sensor blooming when a bright object saturates the detector creates halos that can seem unnatural. Compression algorithms smooth out detail in ways that mimic the look of synthetic imagery. Just because something looks too clean doesn't mean it's fake. It might just mean it's been processed aggressively to pull signal out of noise. The burden of proof, though, sits squarely on the shoulders of whoever is making the extraordinary claim. And right now, that claim is this is an alien spacecraft. If you're asserting that, you need more than a watermarked video clip. You need instrument metadata. You need raw data files. You need independent confirmation from multiple observers at different locations using different instruments. You need spectral analysis showing non-natural emission lines or thermal signatures inconsistent with cometary outgassing. You need trajectory data demonstrating non-gravitational acceleration that can't be explained by sublimating ice. Extraordinary claims require extraordinary evidence. We don't have that yet. The timing amplifies everything. 3i Atlas is about to slip behind the sun from Earth's perspective. We're entering the solar conjunction window, a period where observational geometry makes detailed imaging nearly impossible. This is exactly when false positives are most common. Low signal-to-noise conditions, high glare, instruments pushed to their limits trying to extract faint objects from bright backgrounds. Under those conditions, artifacts multiply. Diffraction spikes can look like structures. Internal reflections can mimic symmetry. Hot pixels can cluster in ways that suggest intentionality. Astronomers know this. They deal with it constantly, and they apply rigorous standards to separate real detections from instrumental ghosts. What do we have from official channels so far? Observations of 3i Atlas from Gemini, Hubble, JUST-T, the Very Large Telescope, and Keck have shown a cometary coma with unusual chemistry. Nothing metallic, nothing craft-like, just a fuzzy cloud of gas and dust surrounding a small solid nucleus. The chemistry is weird, we'll get to that, but the morphology is Comet standard. There are jets, there's a faint tail, there's evidence of outgassing driven by solar heating. That's what you expect from a comet. It's not what you expect from a spacecraft. The media hasn't helped. Tabloid outlets have been running with headlines designed to maximize clicks, not clarity. Stories emphasizing the green glow of the comet, sensationalizing the nickel chemistry, hinting at metals without explaining the natural processes that produce them. We're not going to do that. We're going to keep the facts and the speculation in separate boxes so you can judge for yourself where the line is. So here's where we stand. The leaked image is unverified. It lacks the metadata and multi-source confirmation that would elevate it to evidence. It surfaced at a time and under conditions that make independent verification difficult. The aesthetic features that make it look artificial could also be consistent with heavily processed solar-adjacent imaging. We don't know who made it, where it came from, or whether it's genuine, but we also can't definitively prove it's fake. We're in the fog. What we do have, though, is something else. Another image. This one verified, traceable, posted by a known observer with a track record. An amateur astronomer with a solar telescope who pointed at the right coordinates at the right time and captured something that shouldn't be there if 3I Atlas were just an ordinary comet. That image gives the leak new oxygen. It doesn't prove the leak is real, but it keeps the door open. And that's what makes this story so hard to walk away from. Part 3. How the alleged leak differs from real comet. Imagery. Let's look at what a comet actually looks like when you point a serious telescope at it. Real comets are messy. They're fuzzy. They don't have clean edges or symmetrical profiles. When you image a comet, what you're seeing is a small solid nucleus maybe a few miles across, surrounded by a diffuse cloud of gas and dust called the coma. That coma can stretch tens of thousands of miles in every direction. Behind the nucleus, solar radiation pressure pushes lightweight dust particles away from the sun, creating a tail that can stretch for millions of miles. Sometimes there's a second tail, a plasma tail made of ionized gas, glowing blue from fluorescence. These structures are shaped by solar wind, radiation pressure, and the comet's own rotation. They're dynamic, asymmetric, constantly evolving as the comet moves through space. 3I Atlas has been observed by some of the most powerful telescopes humanity has ever built. The James Webb Space Telescope pointed its infrared eyes at it. Hubble captured optical and ultraviolet spectra. The Very Large Telescope in Chile and the Keck Observatory in Hawaii both obtained high-resolution spectroscopy. All of these observations show the same basic picture. A comet, a fuzzy, diffuse object with a coma and evidence of outgassing. Nothing about those images suggests a solid, rigid structure. Nothing suggests metal. Nothing suggests machinery. But the chemistry is strange. That's worth emphasizing. Astronomers detected cyanide, CN, in the coma of 3I Atlas. Cyanide is common in comets. It's a molecule made of carbon and nitrogen, and it forms naturally in the cold, radiation-soaked environment of interstellar space. What's unusual is the presence of atomic nickel vapor, glowing in the coma at levels higher than you'd expect from a typical solar system comet. Even stranger, the iron lines that usually accompany nickel in vaporized rock are weak or absent entirely. It's like the comet is preferentially releasing nickel without iron, which doesn't make sense if you're just heating up generic rocky material. There's a natural explanation for this, and it involves some elegant chemistry. Under certain conditions, nickel can react with carbon monoxide to form nickel tetracarbonyl. That's a volatile compound, a gas that can form at relatively low temperatures compared to vaporizing pure metal. When sunlight hits nickel tetracarbonyl, it breaks apart, releasing nickel atoms into the coma. Those atoms fluoresce, emitting light at specific wavelengths that telescopes can detect. Iron doesn't form a similar carbonyl compound under these conditions, so you get nickel without iron. The process is unusual, but it's not impossible. It's just chemistry playing out in an environment we rarely get to observe up close. Spectroscopy from Keck and the Very Large Telescope has mapped the spatial distribution of CN and nickel around the nucleus. They show that these emissions are concentrated near the core and extend outward in patterns consistent with sublimation-driven jets. That's comet behavior. If this were a spacecraft venting propellant or leaking coolant, you'd expect different patterns. You'd expect collimated beams, repeating pulses tied to attitude-control burns, or thermal signatures localized to specific emitter points. The spectroscopic data doesn't show that. It shows a nucleus-shedding material as it heats up, exactly like a comet should. Now here's where it gets interesting. There are reports of an anti-tail, a sunward jet. Most comet tails point away from the sun because radiation pressure pushes the dust outward. But some comets develop features that point toward the sun. These aren't true tails in the sense of material being blown backward. They're either jets of material erupting from the sunward face of the nucleus, or perspective effects where a curved dust trail appears to point the wrong direction when viewed from certain angles. Anti-tails are rare, but they're not unprecedented. And for 3I Atlas, the timing of this sunward feature coinciding with perihelion is noteworthy. It suggests active outgassing from the sun-facing hemisphere, which is exactly what you'd expect as the comet heats up. But let's compare that to what the leaked image shows. The leaked clip doesn't show a fuzzy coma. It shows a coherent, elongated object. The alleged lights along its spine don't look like diffuse gas emissions. They look like discrete sources, point-like, arranged with regularity. The overall appearance is rigid, structured, engineered. There's no tail, no envelope of dust, no asymmetric jets spraying off at random angles, just this sleek form, bathed in its own glow, hanging in space like it's parked there. That's not what comets look like. Even in extreme cases, when you image a comet in a specific filter that isolates one emission line, you still see diffuse structures, you see gradients, you see fuzzy boundaries, you don't see hard-edged objects with repeating geometric features. The visual language is completely different. Phase angle and filter choice can change appearance dramatically. If you observe a comet in a blue or green filter that isolates CN emission, you suppress the dust continuum and emphasize the gas. The object can look smaller, brighter, more concentrated. If you apply aggressive deconvolution algorithms to sharpen the image, you can introduce ringing artifacts that create the illusion of structure. If you over-sharpen or denoise too aggressively, natural features can start to look artificial. This is a known problem in image processing. You can make nature look engineered if you're not careful, but even accounting for all of that, the leaked image is hard to reconcile with the established morphology of 3I Atlas. NASA's official trajectory data confirms that the comet is not a threat to Earth. Its closest approach to us is about 1.8 astronomical units, roughly 168 million miles. That's nearly twice the distance from Earth to the Sun. If the leaked image makes the object look close, that's an illusion created by perspective, focal length, and framing. The comet is not nearby. It's not approaching Earth. It's falling toward the Sun, and after perihelion it will swing back out into interstellar space and never return. The geometry is locked in by observations spanning months. There's no ambiguity about where it's going. The question is what it is. Tabloid exaggerations have muddied the water. Headlines claiming the comet is turning green make it sound alien and toxic. In reality, the green glow is from CN, a normal cometary molecule. Claims that the comet is emitting alloys confuse spectroscopic detection of atomic nickel with metallurgy. These distortions feed into narratives that don't match the scientific record. We're going to stick to what's in the peer-reviewed papers and observatory reports. If the data changes, we'll update. But right now, the official story is unusual chemistry, yes. Craft-like morphology, no. Except there's this image, and the image doesn't fit. It shows something that looks nothing like the cometary coma captured by Hubble or JWST or Keck. It shows something that looks designed, and that discrepancy is why this has become a lightning rod. That discrepancy is why people can't let it go. There's one more piece to this puzzle, a maneuver. An orbital trick that could explain why any intelligence would send a probe skimming past the Sun at this exact moment. It's called the Oberth effect, and if you understand it, you understand why the timing of the conjunction window matters so much. Because if you're going to accelerate out of the solar system at maximum efficiency, there's only one place to fire your engines, and that's right where 3I Atlas is going to be in 9 days. Part 4. The Tiago/Dobsonian Power Solar Scope Capture. On October 20th, 2025, an amateur astronomer named Tiago posted a raw frame from his solar telescope. He goes by Dobsonian Power online, a handle that reflects his enthusiasm for large aperture, manually operated telescopes typically used for deep sky observing. But Tiago also maintains solar imaging equipment, and on that morning he pointed his scope at a specific set of coordinates provided by NASA's ephemeris data for 3I Atlas. He captured something. The image shows a compact bright region against the diffuse glow of the solar corona. There's a pronounced forward-facing structure, a shield, as some observers have called it, angled toward the Sun. Behind this bright front section is a faint conical puff of material, asymmetric and less luminous than the leading edge. Critically, there's no extended tail, no long streamer of dust stretching away from the sun, just this concentrated front-heavy form with a short, diffuse wake. This is verified. Data in the sense that Tiago is a known observer with a public track record. His post includes timestamp, coordinates, and equipment details. Other amateur astronomers have cross-referenced his pointing solution with JPL's ephemeris and confirmed that he was indeed looking at the right location at the right time. This isn't an anonymous leak. This is traceable community-level verification. It's not agency-certified, peer-reviewed science data, but it's not nothing either. It's a data point. The raw frame is speckled with coloured noise, hot pixels, cold pixels, sensor artifacts amplified by high gain, and aggressive solar filtration. This is completely normal for solar-adjacent imaging. When you're trying to capture a faint object near the sun, you're pushing your detector to its limits. You crank the exposure time as long as you can without saturating on the solar disk. You crank the gain to pull signal out of the background. And when you do that, all the imperfections in your sensor light up. The result is a grainy, noisy frame that requires careful processing to extract meaningful signal. Tiago posted the raw data, which is exactly what you want to see. Raw means unmanipulated. Raw means you can evaluate the noise characteristics yourself and judge whether what you're seeing is real structure or artifact. What this frame does is confirm that something is there, at the predicted coordinates, at the predicted time, with a morphology that matches neither a typical cometary coma nor the appearance of a background star or galaxy. The front brightening is significant. Most comets brighten uniformly or show jets erupting from the nucleus in multiple directions. A strongly asymmetric forward-facing bright region is unusual. It could be a sunward jet, material erupting from the hemisphere facing the sun as that surface heats up. That would be consistent with the anti-tail reports from spectroscopic observations. The sun-facing side is active, venting gas and dust directly toward the star, creating a compact, bright feature that doesn't have time to disperse before the observer's line of sight cuts through it. Or it could be something else. Forward scattering. When sunlight hits small particles, it scatters in all directions, but there's a preferential scattering angle that enhances brightness when you're looking at the object from a specific geometry. If 3i Atlas has a dust cloud concentrated on its sunward side, and Tiago's viewing angle happened to align with that scattering sweet spot, you'd see exactly this kind of bright leading edge. It's an optical effect, not a physical structure. The brightness isn't intrinsic to the object, it's a consequence of how sunlight interacts with dust particles at that particular phase angle. This effect is well understood in planetary science. It's why the moon looks brighter at full phase than at crescent. It's why Saturn's rings brighten dramatically when Earth crosses the ring plane. Physics, not. Propulsion. But then there's the cone, the faint diffuse structure trailing the bright front region. If this were purely forward scattering, you'd expect the brightness to fall off smoothly with distance from the nucleus. Instead, there's a defined conical shape, like a jet or plume. That suggests directed outgassing, material flowing away from the nucleus in a preferential direction, possibly along the object's rotation axis, or from a localized active region. Comets do this all the time. They develop jets that create asymmetric comae and odd tail structures. What's striking here is the lack of an extended tail. At the distance 3i Atlas is from the sun right now, you'd expect solar radiation pressure to have pushed dust particles into a noticeable tail. The fact that Tiago's image doesn't show one either means the dust production is lower than expected, or the particle size distribution is skewed toward larger grains that don't get pushed as easily, or something about the viewing geometry is hiding the tail. Or, if we're entertaining the alternative hypothesis, there is no tail because this isn't a comet shedding dust. It's a craft venting something for thermal management or propulsion, and whatever it's venting doesn't behave like cometary dust. The chemistry data supports unusual activity on the sunward side. The detection of CN and nickel in the coma, combined with the spatial distribution showing concentration near the nucleus, aligns with the idea that the sun-facing hemisphere is actively sublimating volatiles. The carbonyl chemistry pathway we discussed earlier could be operating at peak efficiency on that side, liberating nickel atoms as the surface heats up. This could produce a localized bright region without requiring any artificial processes. It's weird, but it's plausibly natural. Tiago's image has to be evaluated for artifacts. Solar telescopes deal with seeing conditions, atmospheric turbulence, and thermal ripples that can distort structure. The sun heats the ground, creating convection cells in the air above the telescope. Those cells act like moving lenses, bending light and blurring images. High-cadence imaging and lucky imaging techniques can mitigate this, but the artifacts don't disappear completely. You can get false structures. You can get apparent symmetries that aren't real. The fact that multiple observers, including whoever produced the leaked clip, are reporting similar morphology helps rule out a single-frame glitch. If only one person saw this, you'd dismiss it as artifact. When multiple independent sources report consistent features, it becomes harder to ignore. What this frame does not do is prove that 3i Atlas is artificial. It proves that something anomalous in appearance is present at those coordinates. It confirms that the object's morphology is unusual enough to warrant closer scrutiny. It validates that the leaked clip, whatever its provenance, is at least describing an object that exists in that location. It doesn't tell us what the object is, it just tells us it's there, and it looks strange. NASA's distance and trajectory data remain the anchor. The object is not approaching Earth. It is not on a collision course. The narrative around 3i Atlas is not about impact risk. It's about the possibility, however remote, that we're observing something that doesn't fit the standard model of cometary behaviour. The fact that this is happening right as the object approaches the optimal location for a high-energy manoeuvre is what gives the speculation its teeth. If you wanted to accelerate a spacecraft using the sun's gravity well, you would do it at perihelion. You would fire your engines at the lowest point in your orbit, when you're moving fastest and the gravity gradient is steepest. Every bit of delta V you add at that moment gets multiplied by the depth of the well. It's called the Oberth effect, and it's one of the most efficient tricks in orbital mechanics. And 3i Atlas is going to pass through that exact sweet spot in 9 days, while Earth-based telescopes are blind. Part 5. Why the Oberth maneuver keeps coming up. The Oberth effect is not science fiction, it's orbital mechanics, basic physics that any spacecraft designer learns in their first semester. The principle is simple. If you want to change your energy in orbit, you do it where you're moving fastest. When you fire a rocket engine, the energy you add to your spacecraft depends not just on the thrust of the engine, but on your velocity at the moment you fire it. The faster you're going, the more kinetic energy each unit of propellant adds to your total energy budget. It's counterintuitive, but it's mathematically solid. Firing at the bottom of a gravity well, where your orbital velocity is highest, gives you more bang for your buck than firing in deep space where you're moving slowly. Human missions have used this trick for decades. The Voyager probe swung past Jupiter and Saturn, using gravity assist to steal momentum from the planets and fling themselves toward interstellar space. The Cassini mission used multiple planetary flybys to reshape its trajectory and insert into Saturn orbit. The Galileo probe used Venus and Earth flybys to gain enough energy to reach Jupiter. Every deep space mission that needs a big velocity change thinks about the Oberth effect. It's how you get anywhere in the solar system without carrying impossibly large fuel loads. Now apply that logic to an interstellar probe. If you're an intelligence from another star system and you want to send a reconnaissance craft through the solar system, you'd design its trajectory to maximize science return and maneuverability. You'd want to pass close to multiple planets to observe them. You'd want to sample the local environment, check for biosignatures, map gravitational anomalies, measure the star's magnetic field and radiation output, and when you're done, you'd want to leave, fast, either to return home or to continue on to the next star, or to settle into an orbit where you can loiter and watch. To do any of that efficiently, you'd use the sun. Dr. Avi Loeb, a theoretical astrophysicist at Harvard, has been pointing this out publicly since 3i Atlas was discovered. He's noted a series of anomalies in the object's trajectory and properties that, when taken together, suggest the possibility of deliberate design. First, the trajectory itself. 3i Atlas approached the solar system from a direction close to the ecliptic plane, within about 5 degrees. The ecliptic is where all the planets orbit. It's the busy highway of the solar system. If you're trying to visit planets, you'd aim for that plane. A random interstellar object has no reason to prefer the ecliptic. The galaxy is three-dimensional. Interstellar space is isotropic. An object on a purely ballistic, gravity-only trajectory from another star system should arrive from a random direction in the sky. The fact that 3i Atlas came in near the ecliptic is unusual. Second, the close planetary encounters. 3I Atlas's trajectory brought it within tens of millions of miles of Venus, Mars and Jupiter. Not collisions, but close approaches by interstellar standards. If you wanted to fly by multiple planets on a single pass through the system, you'd design exactly this kind of trajectory. It's efficient, it's opportunistic, it's what a mission planner would do. Third, the mass estimate. Loeb points out that 3I Atlas appears to be more massive than the first two interstellar visitors, 1I/Oumuamua and 2I/Borisov. Mass estimates for comets are model-dependent and uncertain, so this point is debatable, but the claim is that 3I Atlas is carrying more material than you'd expect for an object of its size and activity level. If it's a spacecraft with propellant tanks and structure, that would explain the discrepancy. Fourth, the chemistry. The nickel-over-iron ratio and the low water fraction detected by JWST at large heliocentric distances. Water ice is the dominant volatile in most solar system comets. The fact that 3I Atlas is carbon dioxide rich and water poor is unusual, though not impossible. Interstellar comets could form in environments with different temperature profiles and chemical compositions than our local comets. But it's one more thing that doesn't fit the template. Fifth, the sunward jet. The anti-tail feature. If this is purely natural outgassing, it's happening at a specific location on the nucleus and pointing in a specific direction. That's possible, but it's convenient. It's exactly what you'd see if the object were firing a thruster to adjust its trajectory. Sixth, the timing. 3I Atlas will reach perihelion at a moment when Earth-based telescopes cannot observe it closely. Solar conjunction. The Sun is in the way. This provides a natural cover for any manoeuvring. If the object were to fire its engines during this window, the only way we'd detect it is from spacecraft at different locations in the solar system, observing from angles where the Sun doesn't block the view. SOHO, stereo, maybe some planetary orbiters. But those instruments aren't designed for high-resolution imaging of faint objects. They're designed for solar physics and wide-field surveys. The chances of catching a brief thruster burn are low. By the time 3I Atlas emerges from conjunction and Earth-based telescopes can see it again, the burn would be over. All we'd have is the post-maneuver trajectory, and we'd have to infer the delta V from the difference between the predicted orbit and the observed orbit. And that's the test. That's how we'll know. If 3I Atlas's post-perihelion trajectory matches the gravity-only predictions, the Oberth hypothesis weakens. If there are systematic residuals, if the object ends up in a slightly different orbit than expected, the hypothesis strengthens. Orbital mechanics is precise. You can predict where an object will be months or years in advance based on its current trajectory and the gravitational forces acting on it. Any deviation from that prediction means a force we didn't account for. Outgassing can produce small deviations. Comets do this. The asymmetric venting of gas creates a rocket effect that nudges the comet's orbit. But those nudges are typically small and random. If 3I Atlas shows a large systematic change in its trajectory, something that looks planned, that's when the conversation shifts from interesting comet to we need to talk. NASA says the object is not a threat. Its trajectory keeps it far from Earth. The perihelion distance is 1.4 astronomical units, well inside Earth's orbit but with no intersection. After perihelion, it will swing back out and leave the solar system on its hyperbolic escape trajectory. The Oberth speculation isn't about collision risk. It's about the possibility that what we're tracking isn't following a purely ballistic path. It's about the possibility that something is steering. There are two branches to this speculation, and they lead to very different outcomes. The first branch is acceleration. If 3I Atlas fires its engines at perihelion to add velocity, it could boost itself onto a faster escape trajectory. Maybe it's done with this solar system and wants to head to the next star on a tighter timeline. Maybe it's returning home with data. Maybe it's racing ahead to prepare for something else. An Oberth burn to accelerate out would be the most fuel-efficient way to leave. You'd light your engines right at perihelion when you're already moving at maximum velocity relative to the Sun. Every kilogram of propellant you burn adds maximum energy to your total budget. You leave faster, farther, with less fuel cost than any other maneuver. The second branch is deceleration. This one is more unsettling. If the object fires its engines retrograde against its direction of travel, it can shed velocity, bleed off speed. Instead of escaping the solar system, it could drop into a bound orbit. It could stay here, loiter in the inner system, continue observations, deploy secondary payloads, establish infrastructure. A deceleration burn at perihelion is still efficient because you're burning at high velocity, but the outcome is opposite. Instead of leaving, you're capturing yourself into orbit. You're setting up shop. Both scenarios are speculative. Both require evidence we don't have yet, but both are consistent with the Oberth maneuver as a propulsion strategy. And both explain why the conjunction window matters so much. If you're going to burn your engines, you do it when nobody can see you. You do it when the sun's glare hides your plume. You do it when Earth's telescopes are blind, and the only witnesses are spacecraft that aren't looking for you. Now connect this back to the leaked image. If the evenly spaced bright nodes along the object's spine are real, what could they be? One interpretation is thruster banks, clusters of engines arranged along a spinal truss, designed to provide thrust vectoring and attitude control. Another interpretation is radiator panels. Any propulsion system generates heat. If you're doing a high-energy burn near the sun, you need to dump that heat, or your systems cook. Radiators glow. They emit in the infrared and sometimes invisible wavelengths if they're hot enough. A spacecraft with an active thermal management system could produce exactly the kind of evenly spaced bright nodes people are seeing in the image, or its sensor artifacts, diffraction spikes, internal reflections in the optical path, CCD blooming from a bright, compact nucleus, hot pixels clustering in a pattern that looks deliberate but isn't. The key is the post-perihelion data. When 3I Atlas emerges from conjunction in early November, observers worldwide will be pointing every available telescope at it. They'll measure its position, velocity, and spectroscopic signature. They'll compare the observed trajectory to the gravity-only predictions. If there's a mismatch, if the object has gained or lost velocity in a way that can't be explained by cometary outgassing, the hypothesis gains weight. If the trajectory is unchanged, if the object is exactly where Newtonian mechanics says it should be, the hypothesis collapses. We'll know, not immediately. It takes time to collect enough astrometry to detect small deviations. But within weeks, the orbital analysts will have an answer. In the meantime, we're in the dark, literally. The sun is between us and the object, and we're flying blind. The blackout window is open. If something's going to happen, it's happening now, and we won't know until it's over. This is the core of the Oberth narrative. It's not about proving 3I Atlas is artificial. It's about recognizing that if it were artificial, this is exactly what the mission profile would look like. This is when you'd do the burn. This is when you'd hide it. And the fact that amateur observers are capturing imagery that doesn't look like a comet right before the blackout is what makes people unable to look away. The morphology is strange, the timing is convenient, the chemistry is unusual, the trajectory is opportunistic. None of these things prove intent. All of them invite questions, and in a few weeks, we'll have data that could answer some of those questions, or we'll have more questions. Either way, the next act of this story is about to unfold, and we can't skip ahead. We have to wait. While the object swings past the sun, while Earth's telescopes sit idle, while the conjunction window closes and opens again on the other side, we have to trust that the data will be there when we can finally see again, and we have to be ready for what it might tell us. Part 6. Morphology. Anomaly. Rod-like body with lights. The human brain is an exquisite pattern recognition machine. It evolved to spot predators in the underbrush, to see faces in the shadows, to detect order in chaos because order often meant intention, and intention often meant danger or opportunity. This is why we see animals in clouds and faces in rock formations and apparently spacecraft in cometary images. We are wired to interpret ambiguous visual data as meaningful structure. The question is whether what we're seeing in these images of 3I Atlas is pattern or pareidolia. Is there really something there that doesn't fit natural expectations? Or are we doing what we always do, which is seeing what we want to see? Let's break down the visual claims in detail. The alleged leaked image shows an elongated, spindle-shaped object. The aspect ratio is high. Length significantly exceeds width. It's not a sphere. It's not an irregular potato shape. It's a rod. Along the central axis of this rod are discrete bright points. Not a continuous glow. Not random scattering. Discrete nodes, evenly spaced, each with similar brightness and colour. The spacing looks deliberate, geometric. If you drew lines connecting them, you'd get a straight spine with regular intervals. That's the first red flag for the human visual system. Regular spacing in nature is rare. Crystals do it. Molecular structures do it at microscopic scales. But macroscopic objects, especially ones made of ice and rock, don't tend to self-organize into evenly spaced glowing dots. Then there's the sheath. A blue-white glow wrapping the entire object, creating a halo effect that enhances the sense of symmetry. It's uniform. The brightness doesn't vary much from one end to the other. There's no obvious nucleus, no single bright core that you'd expect from a comet, with a solid reflective surface surrounded by diffuse gas. Just this smooth, distributed luminosity that makes the whole structure look like it's illuminated from within, or like it's emitting light rather than reflecting it. If you were designing a spacecraft for interstellar travel, what would it look like? The answer depends on your engineering constraints. Speed is one constraint. If you're moving at a significant fraction of light speed, you need shielding up front to absorb impacts from interstellar dust and gas. A Whipple shield, named after astronomer Fred Whipple, is a multi-layered bumper system designed to vaporize incoming particles before they hit critical systems. You'd place this at the bow, the leading edge, oriented in your direction of travel. That would create a bright reflective or ablative surface facing forward. If sunlight hits that surface at the right angle, it glows, it stands out. Behind the shield, you'd have a spinal truss, a load-bearing structure running the length of the craft, connecting propulsion at one end to payload and sensors at the other. Along this truss, you'd mount systems, fuel tanks, power generators, radiators, communication arrays, maneuvering thrusters. Each of these systems has its own thermal signature. Radiators, in particular, need to be distributed along the structure to efficiently dump heat. If your power system is running hot, if you're doing a high-energy maneuver, those radiators glow. They emit an infrared primarily, but if they're hot enough, they can emit visible light. A spacecraft with an active thermal management system, viewed from a distance, could look exactly like a rod with evenly spaced glowing nodes. Maneuvering jets are another possibility. If you're doing fine attitude control, keeping your orientation stable or adjusting your spin rate, you'd use small thrusters arranged around the vehicle's center of mass. Fire them in sequence, and they create a pattern of bright flashes. If someone captures a long exposure image while you're actively maneuvering, those flashes integrate into bright spots. The spacing depends on your thruster layout, but symmetry is desirable for balance. Engineers like symmetry. It simplifies control algorithms, so you'd place thrusters at regular intervals, and that's what an observer would see. But let's consider the natural alternatives. Could a comet produce this appearance without being artificial? Start with the geometry. Comets are not usually elongated rods, but they can be. 1I/Oumuamua was estimated to have an aspect ratio of 10:1, a cigar-shaped tumbling rock. If 3I Atlas is similarly elongated, and if we're viewing it nearly along its long axis, end on, it could appear as a narrow spindle. The question is whether that's consistent with the observed rotational light curve and the spectroscopic data, which suggest a more typical cometary shape. Next, the bright nodes. Could these be jets seen end on? Comets develop active regions on their surfaces where sunlight sublimates ice and drives gas and dust into space. If 3I Atlas has multiple jets erupting from along its rotation axis, and if we're viewing those jets head-on, each jet could appear as a bright spot. The spacing would depend on where the active regions are located, which is controlled by surface geology and rotation state. Random in principle, but possibly clustered if there's some underlying structural pattern in the nucleus, like fracture lines or compositional boundaries. It's not impossible. It's just unlikely to produce the kind of regularity people are reporting. Forward scattering is another mechanism. When sunlight hits small dust particles, it scatters preferentially in the forward direction. If 3I Atlas has a dusty coma concentrated around the nucleus, and if the viewing geometry aligns with a forward scattering angle, the whole coma lights up. But forward scattering tends to produce a smooth, diffuse glow, not discrete points. To get point-like features, you'd need clumps of dust, concentrations separated by voids. That could happen if the comet's outgassing is episodic, puffing out material in bursts rather than continuously. Each puff creates a denser region, and those regions scatter light more efficiently. Seen from a distance, they could look like nodes. But the spacing would be irregular, changing as the puffs expand and disperse. The fact that multiple images show consistent node positions argues against this unless the puffs are being replenished at the same locations, which brings us back to fixed active regions and makes the natural explanation more contrived. Deconvolution artifacts are a real concern. When you process astronomical images to sharpen detail, you're mathematically inverting the point spread function of your telescope. This amplifies real structures, but also amplifies noise. If you're not careful, you can create false structures, ringing around bright sources, phantom edges, repeating patterns tied to the symmetry of your PSF. Professional astronomers apply deconvolution cautiously and validate the results against raw data. If the leaked image has been heavily processed, if someone pushed the sharpening too far, the nodes could be artifacts. But the raw Tiago frame also shows front brightening, and it's not heavily processed. So either multiple independent processing pipelines are producing similar artifacts, which is suspicious, or there's real structure there. The chemistry of 3I Atlas adds another layer. The nickel cyanide anomaly. Carbonyl chemistry can explain atomic nickel without iron, but it's unusual. It requires specific temperature and pressure conditions. The fact that this chemistry is happening at all suggests active volatile processing near the nucleus. Nickel tetracarbonyl forms at relatively low temperatures when nickel-bearing minerals interact with carbon monoxide. Sunlight breaks it apart, releasing nickel atoms. Those atoms fluoresce, emitting at specific wavelengths. If the nickel emission is concentrated in specific regions, either because the active areas have more nickel-rich material or because the temperature distribution is uneven, you could get bright spots in nickel-filtered images. That's a natural process. But it's also exactly what you'd see if a spacecraft were venting something nickel-rich as part of its thermal or propulsion system. Filter choice matters enormously. If you image 3I Atlas in a filter that isolates CN emission, you're seeing only the gas, not the dust. The coma collapses visually, becoming smaller and brighter. Active regions stand out. If you image in infrared, you're seeing thermal emission from warm dust. The appearance changes completely. If you image in visible light with no filter, you're seeing reflected sunlight from the nucleus and dust, plus gas fluorescence. The object looks fuzzy and diffuse. The leaked image appears to be in blue or white light, emphasizing the symmetry and smoothness of the sheath. The Tiago frame is likely filtered for solar observation, suppressing certain wavelengths to avoid sensor saturation. Each filter tells a different story. The trick is figuring out which story is true. Phase angle also plays a role, the angle between the sun, the object, and the observer. At certain phase angles, small particles exhibit opposition surge, a sudden increase in brightness when sunlight backscatters directly toward the observer. This can make a dusty coma look artificially bright and create the illusion of a shiny metal surface. Conversely, at other phase angles, the same particles look dark. If 3I Atlas is at a phase angle, where forward scattering or opposition surge is strong, natural materials can mimic reflective metal. This is well documented in planetary science. Icy moons, dusty rings, even the lunar regolith all show phase-dependent brightness effects that can be mistaken for intrinsic material properties. Spin state is testable. If 3I Atlas is tumbling, the bright nodes should rotate in and out of view as the object spins. Their positions should shift over time in a predictable pattern tied to the rotation period. If the nodes are fixed to the surface, they'll move. If the nodes are artifacts tied to the observer's telescope or processing algorithm, they won't. If the nodes are radiators or thrusters on a spacecraft that's maintaining a fixed orientation, they also won't move, but for a different reason. High-cadence photometry can distinguish these cases. Take a series of images over several hours, track the nodes, and see if they rotate. That's a falsifiable test. If nobody's done it yet, they will. We've been here before. 1I/Oumuamua was elongated. It tumbled. It accelerated in a way that didn't match gravity alone. For 2 years, scientists debated whether it was a comet with asymmetric outgassing or something else. Some proposed it was a hydrogen iceberg. Some suggested it was a fragment of a shattered exoplanet. One paper, authored by Avi Loeb and his then postdoc Shmuel Bierli, suggested it could be a light sail, a thin, reflective membrane pushed by starlight. That paper ignited a firestorm, not because it was irrational, but because it crossed a line. It entertained the possibility of artificial origin without extraordinary evidence. The scientific community pushed back hard. The consensus settled on weird comet with low outgassing rate, and most researchers moved on. But the debate illustrated how appearance can mislead us. elongation doesn't mean artificial, unusual acceleration doesn't mean propulsion. And yet the questions linger, because we don't have a good natural explanation for everything One Eye saw and did. We have plausible explanations, but not definitive ones. And now we're looking at Three Eye, and the same questions are back louder this time. The way forward is multiband, high-cadence photometry. Image the object in multiple filters simultaneously. Track the brightness and colour of each alleged node over time. Look for rotation. Look for variability. Look for spectral lines that match known molecules or emit in ways consistent with artificial lighting. Compare the point spread function of the nodes to that of nearby stars. If the nodes are real physical features, their PSF should match the stars. If they're artifacts, their PSF will be distorted. This is forensic astronomy, treating the image as a crime scene and reconstructing what happened from the evidence left behind. And if the evidence shows that the nodes are real, that they don't rotate, that they emit light in ways inconsistent with cometary chemistry, then we have a problem. Because that would mean Three Eye Atlas is not a comet. It would mean we're observing something that doesn't fit any natural category we have. And we'd have to decide what to do about that. But first, we need to talk about timing, because the morphology anomaly is only part of the story. The trajectory is the other part, and when you look at where Three Eye came from, how it moved through the solar system, and where it's going, the coincidences start to pile up. Part 7. Timing and Trajectory Oddities. Let's talk about where Three Eye Atlas came from and why that matters. Interstellar space is big, unimaginably big. The nearest star system to our Sun, Alpha Centauri, is 4.3 light-years away. That's 25 trillion miles. If you picked a random direction in the sky and threw a rock, the odds of it hitting our solar system are effectively zero. Space is mostly empty. Stars are tiny targets separated by oceans of nothing. For an object to arrive at our Sun from interstellar space, it has to be aimed. Either it's aimed by gravity, perturbed by the galactic potential and stellar encounters over millions of years until it happens to intersect our system, or it's aimed intentionally, launched on a trajectory designed to reach us. Random interstellar objects arrive from random directions. The galaxy is three-dimensional. There's no preferred orientation. The plane of the Milky Way is flat on galactic scales, but on the scale of individual star systems, there's no reason an incoming object should align with anything in particular. It should come from above or below the ecliptic as easily as from within it. The ecliptic, remember, is the plane in which Earth and the other planets orbit the Sun. It's defined by the angular momentum of the solar nebula that formed the planets 4.6 billion years ago. It's our plane. It's parochial to our system. An interstellar visitor has no business caring about it. And yet, Three Eye Atlas approached from a direction within about 5 degrees of the ecliptic. Avi Loeb has pointed this out repeatedly. 5 degrees is close, not exact, but close enough that if you were planning a tour of the solar system's planets, you'd aim for that geometry. The planets all orbit within a few degrees of the ecliptic. If your goal is to fly by multiple planets on a single pass through the system, you'd inject into a trajectory that crosses the ecliptic plane at a shallow angle. That way, you maximize your chances of encountering planets without needing large course corrections. It's Mission Design 101, efficient, opportunistic. Exactly what you'd do if you had limited propellant and wanted to see as much as possible. Three Eye Atlas's trajectory brought it close to Venus, Mars and Jupiter. Not collision close, but within tens of millions of miles. For Venus and Mars, that's a close encounter by interstellar standards. For Jupiter, it's a distant pass, but still within the gravitational influence of the planet. If you're a reconnaissance probe, these are prime targets. Venus to study runaway greenhouse atmospheres, Mars to check for extinct or extant life, Jupiter to sample the magnetosphere and observe the Galilean moons. You'd want to pass near all of them, and Three Eye Atlas's trajectory does exactly that. Now, you might argue that this is selection bias. We only notice interstellar objects that come close to the Sun because those are the ones we can detect. Objects that pass through the outer solar system without approaching the inner regions stay too faint for our surveys. So maybe there are hundreds of interstellar visitors every year, and we only see the ones that happen to come close enough and at the right geometry to be discovered. That's a valid point. Our detection efficiency is biased toward objects that approach the Sun and brighten from solar heating. But even accounting for that bias, the ecliptic alignment is unusual. There's a broad range of possible trajectories that would bring an object close to the Sun, and most of them don't align with the ecliptic. The fact that 3i Atlas does is a statistical outlier. Not impossible, just unlikely. The perihelion distance and timing add to the oddity. Perihelion occurs around October 29th or 30th, 2025, at a distance of approximately 1.36 to 1.4 astronomical units from the Sun. That's inside Earth's orbit, but outside Venus's orbit. It's a sweet spot. Close enough to the Sun for significant solar heating, which would activate any icy volatiles and make a comet brighten dramatically, but not so close that the object risks structural damage from thermal stress. If you're trying to do a high-energy maneuver, you want to get as close to the Sun as you can without cooking your spacecraft. 1.4 AU is reasonable for that. It's hot, but manageable with proper heat shielding. The closest approach to Earth is about 1.8 AU, roughly 168 million miles. That's farther than the Sun, so there's no danger of collision or even a close pass. The geometry places Earth off to the side while 3i Atlas dives toward the Sun. But from Earth's perspective, the object and the Sun are nearly aligned in the sky during perihelion. That's solar conjunction. The Sun's glare overwhelms any faint object nearby. It's the same reason we can't observe Mercury and Venus when they pass behind the Sun from our vantage point. The Sun is too bright. The contrast is too high. Our telescopes and cameras can't separate the faint object from the overwhelming foreground. Solar conjunction happens routinely in spaceflight operations. When Mars or a Jupiter-bound spacecraft passes behind the Sun as seen from Earth, we lose communication for days or weeks. NASA's Deep Space Network can't maintain a radio link because the Sun's radio emission drowns out the spacecraft's signal, and solar plasma distorts the transmission. Mission planners design around these blackout windows. They upload command sequences in advance, put the spacecraft into a safe mode, and wait for conjunction to end before resuming operations. It's a known operational constraint, and it's the perfect cover for any maneuver you don't want observed. If 3i Atlas were a spacecraft, and if it intended to perform an Oberth burn at perihelion, the conjunction window provides natural operational security. Earth-based telescopes can't see you. Earth-based radar can't track you. Radio observatories can't detect emissions because the Sun's radio output is overwhelming at those frequencies. You're hidden. Not invisible to spacecraft at other locations in the solar system. SOHO, stereo. Maybe some planetary orbiters could catch glimpses depending on their geometry. But those platforms aren't optimized for high-resolution imaging of fast-moving faint objects. Their primary missions are solar observation or planetary science, not tracking comets. The odds of catching a transient thruster burn are low, unless someone is specifically looking for it. Then there's the sunward anti-tail. Multiple spectroscopic observations have reported a jet or extension of the coma pointing toward the Sun. Anti-tails are rare in comets. Normally, radiation pressure pushes dust away from the Sun, creating tails that point in the anti-solar direction. A sunward feature suggests either active outgassing from the sun-facing hemisphere, which is plausible given that's the side receiving the most heating, or a perspective effect where a curved dust trail appears to point the wrong direction when viewed from certain angles. But perspective effects are usually transient. They change as the observer's geometry changes. If the sunward feature persists across multiple observations from different dates and viewing angles, it's more likely a real physical structure, a jet. Material flowing out from the nucleus toward the Sun. Why would a comet do that? Sublimation-driven jets usually follow the local temperature gradient. The hottest parts of the nucleus vent the most material. On the day side, the sun-facing hemisphere, you'd expect strong outgassing. If that outgassing is concentrated in a jet rather than distributed evenly, and if the jet happens to point along the Sun-comet line, you'd get a sunward extension. It's not common, but it's not impossible. The alternative interpretation is that the object is firing a thruster, specifically a forward-facing thruster designed to slow it down. If you're doing a retrograde burn to shed velocity and capture into a bound orbit, your engine exhaust would point forward, along your direction of travel, and depending on your orientation, that exhaust could be directed sunward. Either explanation is consistent with the observations. The question is which one is more likely. The mass estimate is contentious. Loeb claims 3i Atlas is more massive than 1i/Oumuamua or 2i/Borisov. Mass estimates for comets are derived from brightness, assumed albedo, and dynamical behavior. All of these are model-dependent. If you assume the object is a porous ice dust mix with typical cometary albedo, you get one mass. If you assume it's denser, more compact, with higher albedo, you get a different mass. If you include structure, like internal tanks or machinery, the mass goes up. The uncertainty is large. But if the object is genuinely more massive than expected for its size and activity level, that's another data point that doesn't quite fit the standard comet model. After perihelion, the test becomes clear. Observers will track 3I Atlas's position as it moves away from the Sun. They'll compare the observed trajectory to the predictions based on gravity alone. Orbital mechanics is deterministic. If you know an object's position, velocity, and the gravitational forces acting on it, you can predict its future trajectory with high accuracy. Any deviation from that prediction indicates an unmodelled force. For comets, that force is usually outgassing. The asymmetric venting of gas creates a small rocket effect. It's random, noisy, and typically small. If 3I Atlas shows a systematic deviation, a change in velocity that's larger than expected from outgassing, and points in a specific direction, that's evidence of something else. If the deviation is consistent with an Oberth burn, either accelerating out or decelerating into a bound orbit, the hypothesis gains teeth. The observational limitations are significant. During conjunction, Earth-based telescopes are blind. Space assets like the Solar and Heliospheric Observatory and the Solar Terrestrial Relations Observatory might catch the object in their wide-field images. SOHO's LASCO coronagraphs are designed to block the Sun's disk and image the corona, which is exactly the region 3I Atlas will pass through. Stereo has similar capability from different vantage points, but these instruments have limited spatial resolution and sensitivity. They're optimized for bright comets that sun graze within a few solar radii. 3I Atlas at 1.4 AU is much farther out. It might be too faint to detect or too small to resolve. We won't know until the data is processed and released, and that could take weeks. The timing is maddening. If you wanted to witness the most critical moment, the potential Oberth burn, you can't. The geometry won't allow it. The Sun is in the way. You're forced to wait, forced to trust that post-perihelion astrometry will reveal what happened. And in the meantime, the speculation runs wild because there's no new data to constrain it. The blackout window is open, the object is at perihelion right now, or within days, depending on when you're watching this. And we're sitting here, blind, wondering what's happening 93 million miles behind the Sun. NASA's official statements emphasize safety. No threat to Earth. The trajectory is well understood. The object will pass and leave. There's no impact risk. That message is critical. The last thing anyone wants is public panic over a misunderstood cometary visitor. But the reassurance about safety doesn't address the deeper question. Is this just a comet, or is it something else? And if it's something else, what does that mean for us? The next part of this story is about secrecy, about the possibility that higher resolution data exists and isn't being released, about the reasons, benign or otherwise, why information might be withheld. Because if there's one thing that fuels conspiracy theories faster than ambiguous data, it's the perception that someone, somewhere, knows the truth and isn't telling. Part 8. Cover-up. Hypothesis. Why would data be withheld? Let's start with the boring reasons, the ones that don't involve shadowy government agencies or interstellar diplomacy. The reasons why scientific data might not be immediately available to the public even when something interesting is happening. First, data quality. Not every observation is good enough to publish. Astronomical images can be degraded by poor seeing, clouds, equipment malfunction, calibration errors, or bad luck. If you point a telescope at 3I Atlas and the atmosphere is turbulent, your image will be blurry. If the object is too faint, your signal-to-noise ratio will be terrible. If you miscalculate the pointing coordinates, you'll image the wrong patch of sky. Professional astronomers deal with this constantly. They take multiple exposures, throw out the bad ones, and only publish the good ones. If an observatory captured something ambiguous, something that looks interesting but isn't scientifically rigorous, they might hold it back until they can confirm it with better data. That's not a cover-up. That's quality control. Second, calibration. Raw telescope data is messy. It includes instrumental artifacts, dark current, bias frames, flat field variations, hot pixels, cosmic ray hits. Before you can analyze the science target, you have to subtract all of that noise, Calibration can take days or weeks depending on the complexity of the instrument and the expertise of the team. If someone captured 3I Atlas during perihelion, but they're still working through the calibration pipeline, the data won't be public yet. Patience is required. Science doesn't happen in real time. Third, proprietary periods. Many observatories grant the observers who requested the telescope time a proprietary period during which they have exclusive access to the data. This gives them time to analyse the results, write a paper, and submit it to a journal before anyone else can scoop them. Proprietary periods can last months or even a year. It's a standard practice designed to reward the effort of writing a successful observing proposal. If someone has proprietary data on 3I Atlas, they're not obligated to release it immediately. Eventually, the data becomes public, but not right away. Fourth, spacecraft safety. If the relevant data comes from a space-based observatory like JWST or Hubble, the operations teams prioritize the health of the spacecraft over any individual science target. During solar conjunction, some spacecraft go into safe mode to protect their instruments from solar heating or to avoid risky pointing geometries. If imaging 3I Atlas during perihelion would require pointing too close to the Sun, the observatory won't do it. The risk of damaging expensive hardware outweighs the science return, so the data you want might simply not exist because the observation was deemed too risky. Those are the benign reasons. They're mundane. They're how science actually works. They don't make for exciting narratives, but they're statistically the most likely explanation for why high-resolution imagery of 3I Atlas at perihelion isn't flooding the internet right now. Now let's consider the less benign possibilities. The scenarios where information is withheld not because of technical or procedural reasons, but because someone decided it shouldn't be public. National security. If 3I Atlas were determined to be artificial, that information would have strategic implications. It would confirm that interstellar travel is possible and that someone achieved it. It would raise questions about intent. Is this pro-passive or active? Is it observing us or interacting with us? Is it alone or part of a larger fleet? These questions have defense implications. Governments might decide that public disclosure should be delayed until there's a clearer understanding of what's happening and what the appropriate response should be. That's not necessarily nefarious, it's risk management. In the absence of complete information, caution is rational, fear of panic. The history of public reactions to astronomical discoveries is mixed. When Halley's comet passed through Earth's orbit in 1910, tabloids claimed the comet's tail contained poisonous gases that would kill everyone. People panicked. Some sealed their homes, some bought gas masks. None of it was justified. The tail was so diffuse it had no effect on Earth. But the panic was real. If 3I Atlas were announced as a potential artificial object without conclusive evidence, the same kind of hysteria could erupt. Governments and institutions might decide that avoiding panic justifies temporary withholding of ambiguous data. Again, not necessarily a cover-up in the sinister sense, just a judgment call about public communication, confirmation before disclosure. Imagine you're an astronomer who captured an image of 3I Atlas that looks artificial. You're excited. You're also terrified of being wrong. If you release it and it turns out to be an artifact or a misinterpretation, your career is damaged. You become the person who cried alien. Professional reputation matters in science, so you sit on the data, you show it to trusted colleagues, you request follow-up observations from other telescopes, you wait for confirmation, and while you're waiting, the data isn't public. This is human nature. It's not malicious. It's self-preservation, interagency politics. Space science is international. Multiple agencies, observatories and institutions are tracking 3I Atlas, NASA, ESA, JAXA, individual university groups. If one of them has extraordinary data, there might be negotiations about how and when to release it. Who gets credit? Whose press release goes first? What the messaging should be? These negotiations take time. They can delay public disclosure even when there's no intent to suppress information permanently. Bureaucracy and coordination are slow. Now the Japanese origin claim for the leaked image. If that's true, if the clip really did come from a Japanese source, what would that source look like? JAXA operates space missions, but none currently positioned to observe 3I Atlas at high resolution during perihelion. Japan's national observatories have ground-based telescopes capable of solar and near-solar observations. The Hida Observatory, for example, operates solar telescopes. University networks have smaller instruments. Any of these could theoretically have captured something. But if they did, and if it was significant, you'd expect an official announcement. The absence of one suggests either the clip didn't come from an official source, or the source doesn't want to be identified. What would a real leak look like? In professional astronomy, data is stored in FITS format, Flexible Image Transport System. It's a standardized file format that includes not just the image but also extensive metadata. Every FITS file has a header that tells you the telescope, the instrument, the filter, the exposure time, the observation date, and time down to the second, the right ascension and declination of the pointing center, the detector temperature, the gain settings, the observer's name, the program ID. It's a forensic goldmine. If someone leaked a FITS file, astronomers could verify its authenticity within hours. They'd check whether the star field matches the claimed coordinates. They'd verify the point spread function against the known optical characteristics of that telescope. They'd check whether weather records from that night support the seeing conditions implied by the image quality. A real leak would be verifiable. What we have instead is a processed video clip with a watermark. No FITS header, no metadata, no way to trace it back to a specific instrument or observation. That's suspicious. It's consistent with either a hoax, where someone created the clip and added a fake watermark to give it credibility, or a deliberately sanitized leak, where someone stripped the metadata to protect the source. Both scenarios are possible. Neither can be ruled out. Commercial satellite data is another angle. Private companies operate Earth observation satellites with high-resolution cameras. Some of those satellites could theoretically be pointed at solar-adjacent targets if the geometry allows and the customer requests it. Commercial imagery doesn't go through the same public release pipelines as academic data. If a private entity captured something unusual, they might sit on it for business reasons, strategic reasons, or contractual obligations. This creates a data gap. Non-traditional sources producing observations that never enter the public domain. It complicates provenance and makes verification harder. There's also the possibility of intelligence assets. Military and intelligence satellites have capabilities that exceed publicly known civilian instruments. They're designed for Earth observation, but some have the flexibility to point at other targets. If such an asset captured 3I Atlas at perihelion, that data would be classified. It wouldn't be released through scientific channels. It might not be released at all. And if it leaked, it would leak through intelligence communities, not astronomy forums. The watermark, the anonymity, the lack of metadata, all of that is more consistent with an intelligence leak than a scientific one. But here's the thing. Even if data is being withheld, even if there's a short-term holdback for quality control or interagency coordination or national security review, that doesn't automatically imply aliens. Institutions delay information release for all sorts of reasons. The conjunction timing and the viral clip create a perfect storm for cover-up narratives, but narratives aren't evidence. The way to evaluate this is to watch what happens next. If post-perihelion data comes out quickly, if multiple observatories publish their results in peer-reviewed venues, if the trajectory shows no anomalies, then the withholding hypothesis collapses. If, on the other hand, months pass with no new data, if freedom of information requests go unanswered, if observatories that should have captured the object claim they didn't observe it, or that their data was corrupted, then the hypothesis strengthens. We're going to privilege peer-reviewed sources and official agency statements for hard facts. When we speculate, we'll label it clearly. That's the ethos of this video. We're not here to push a conclusion. We're here to map the territory, show you where the data ends and the speculation begins, and let you draw your own conclusions. But before we dismiss the natural object explanation entirely, we need to examine it rigorously. Because there are scientists who've looked at 3I Atlas and seen nothing that requires artificial origin. There are natural mechanisms that can explain the chemistry, the morphology, the trajectory. We owe it to the story to present those mechanisms fairly, to show what it would take for this to be just a comet. A weird comet, but still a comet. Part 9. Natural object counters and what would falsify. Craft. Let's build the case for 3I Atlas as a natural object. Let's see how far we can get before the data forces us to admit we don't know. Start with the chemistry. Multiple spectroscopic observations have confirmed the presence of cyanide and atomic nickel in the coma. Cyanide is normal. It's one of the most common molecules detected in comets. It forms from carbon and nitrogen in the cold molecular clouds where comets are born. When a comet approaches the Sun, solar ultraviolet light breaks apart larger molecules, liberating cyanide into the coma where it fluoresces and becomes detectable. Nothing strange about that. Nickel is less common but not unprecedented. Several comets have shown metal emissions: calcium, sodium, iron, nickel. These metals are present in the rocky and metallic grains embedded in the comet's ice. When the ice sublimates, it exposes these grains to sunlight. The grains heat up. At high enough temperatures, the metals vaporize, releasing atoms into the coma. Those atoms absorb sunlight and re-emit it at characteristic wavelengths, creating emission lines that spectrographs can detect. The puzzle is why nickel is prominent but iron is weak or absent. In typical rocky material, iron is more abundant than nickel. The Sun's composition reflects the overall composition of the solar nebula, and in the Sun, iron outnumbers nickel by about 20 to 1. If 3I Atlas was simply vaporizing generic rocky grains, you'd expect strong iron lines and weaker nickel lines. Instead, you see the opposite. That's the anomaly. The carbonyl chemistry explanation is elegant. Under certain conditions, nickel reacts with carbon monoxide to form nickel tetracarbonyl. This is a well-known compound in industrial chemistry. It's a gas at room temperature, highly toxic, and thermally unstable. When heated or exposed to ultraviolet light, it decomposes, releasing nickel atoms and carbon monoxide. The key is that nickel forms this carbonyl compound much more readily than iron does. Iron carbonyls exist, but they require different conditions. If the temperature and pressure in the comet's near-surface layers fall within a specific range, nickel carbonyl can form and then photodissociate, pumping nickel atoms into the coma without a corresponding increase in iron. This process can explain the nickel-over-iron ratio naturally. Several peer-reviewed papers on 3I Atlas have discussed this mechanism. They've modelled the thermal and chemical environment near the nucleus and shown that carbonyl chemistry is plausible. It requires a carbon monoxide-rich environment, which JWST observations suggest is the case. 3I Atlas is CO2-rich and water-poor at large heliocentric distances. That's unusual for solar system comets, but not impossible for an interstellar object formed in a different stellar environment. The chemistry, while strange, has a natural pathway. The sunward anti-tail has a proposed thermodynamic explanation as well. When the sun-facing hemisphere of a comet heats up, it sublimates volatiles preferentially from that side. If the sublimation is vigorous enough, it creates a jet of gas and dust flowing away from the surface. If that jet happens to be oriented along the sun-comet line pointing sunward, it creates a feature that looks like an anti-tail. The jet isn't actually travelling toward the sun, it's travelling away from the nucleus, but because the nucleus is between the sun and the observer, the jet appears to extend sunward. It's a geometry effect combined with active outgassing. This has been observed in other comets. It's rare, but it's natural. The water budget is another point. JWST detected low water abundance at large heliocentric distances. That's unusual for solar system comets, which are typically ice-rich. But interstellar comets might form in environments where water ice is less abundant. Different temperature profiles in different protoplanetary disks lead to different volatile inventories. A comet formed in a system where carbon dioxide or carbon monoxide dominated over water ice would naturally have a low water fraction. It's not standard, but it's within the range of astrophysical possibilities. Diversity is expected in a galaxy full of planetary systems with different formation histories. Now, the dynamics. The ultimate test of the Kraft hypothesis is the trajectory. If 3I Atlas's post-perihelion orbit matches the gravity-only predictions, that's strong evidence it's a natural object. Non-gravitational forces from outgassing can produce small deviations, but those deviations are typically random and small in magnitude. If the observed trajectory after perihelion stays within the uncertainty envelope of the gravitational model, there's no need to invoke propulsion. The object is following Newton's laws. It's a comet. Outgassing torques can change a comet's rotation state and induce small orbital perturbations. This is well documented. When gas jets erupt from the surface, they exert a force on the nucleus. If the jets are asymmetric, the force creates a torque that changes the spin. If the jets have a net component along or against the direction of travel, they change the orbit. These effects are small but measurable. Astronomers model them by tracking the comet over time and fitting a force model that includes both gravity and non-gravitational accelerations. For 3I Atlas, if the non-gravitational acceleration is consistent in magnitude and direction, with cometary outgassing, the natural explanation holds. Photometry is another test. If the alleged lights are real, they should behave like physical features attached to the object. They should rotate with the nucleus. They should maintain consistent brightness and colour. They should show up in multiple filters. If instead they behave like point spread function artifacts, if they track with the seeing conditions and change from exposure to exposure in ways that don't correlate with the object's rotation, that argues for instrumental effects. High-cadence photometry over multiple nights can distinguish these cases. It's a falsifiable test. If the data shows artifact behaviour, the lights aren't real. If the data shows rotation-correlated behaviour, they're real, and then the question becomes what they are. Thermal physics offers another natural mechanism for the bright leading edge. Small dust particles scatter sunlight efficiently in the forward direction. If 3I Atlas has a dust coma concentrated on the sunward side, and if the particle sizes and viewing geometry are right, forward scattering can make that side appear much brighter than the rest of the coma. This is phase angle dependent. The brightness should change as the phase angle changes. If observers track the object through different phase angles and see the predicted brightness variations that supports the scattering explanation, if the brightness stays constant regardless of phase angle, that argues against scattering and for intrinsic emission. History is full of comets that looked strange. Comet Linear fragmented in 2000, producing a train of debris that looked structured and geometric in some images. Comet Ison disintegrated at perihelion in 2013, creating a knife-edge dust feature that appeared artificially sharp. Comet Shoemaker-Levy 9 broke into fragments that looked like a string of pearls before impacting Jupiter in 1994. In each case, the unusual appearance had a natural explanation. Fragmentation, tidal forces, differential sublimation, dust dynamics. Nature can produce shapes and structures that look engineered if you don't understand the underlying physics. The burden is on us to distinguish engineered from merely unusual. The burden of proof for the craft hypothesis is high. You'd need to demonstrate non-gravitational acceleration that can't be explained by outgassing. You'd need resolved structure in multiple independent images that shows symmetry and regularity inconsistent with natural processes. You'd need spectroscopic signatures that don't match known cometary chemistry. Ideally, you'd want narrowband emission at frequencies consistent with technological sources, radio carriers, laser lines, microwave beams, something unambiguous. None of that has been reported officially. All we have is morphology and timing, which are suggestive but not conclusive. What would change the skeptic's mind? A documented delta V, a change in velocity that's larger than outgassing can produce, and points in a direction consistent with deliberate maneuvering. If 3I Atlas emerges from perihelion on a trajectory that shows a systematic deviation, a change in orbital energy or angular momentum that requires forces outgassing can't provide, that's evidence. If the deviation is in the direction you'd expect from an Oberth burn, either accelerating out or decelerating into a bound orbit, that's stronger evidence. If multiple independent observers confirm the deviation and can't explain it with natural mechanisms, you're approaching proof. Resolved structure from multiple instruments would also be compelling. If Hubble, JWST, VLT, and Keck all capture images showing the same elongated, node-covered morphology, and if those images can't be explained by PSF artifacts or processing errors, you have to take it seriously. If the structure shows internal detail, if there are features that look like joints, panels, antennas, emitters, things that have no business being on a comet, the natural explanation collapses. Spectroscopy could be definitive. If someone detects emission lines that don't match any known cometary molecule or atomic transition, that's a red flag. If those lines are narrowband, indicating a non-thermal source, that's a bigger red flag. If the lines are modulated, pulsed, or structured in ways that suggest information encoding, you're done. You've detected technology. But we're not there. The spectroscopy so far shows CN and nickel, both of which have natural explanations. Skepticism is not cynicism. Skepticism is the scientific method. You start with the null hypothesis. This is a natural object. You collect data. You test whether the data is consistent with the null hypothesis. If it is, you keep the null hypothesis. If it's not, you revise. The natural object explanation for 3i Atlas is strained but not broken. The chemistry is unusual but explainable. The morphology is odd but potentially consistent with viewing geometry and processing artifacts. The trajectory is opportunistic but not impossible for a random interstellar visitor. We're in the grey zone. The data doesn't definitively prove natural origin, but it doesn't definitively prove artificial origin either. The responsible position is to remain open to both possibilities while demanding high-quality evidence before accepting the extraordinary claim. We can enjoy the what-ifs, we can explore the implications, but we can't let speculation override the need for rigour. And right now, the data quality isn't there. We're working with leaks, anonymous clips, amateur images, and incomplete spectroscopy. It's tantalising, but it's not sufficient. Which brings us to the hardest question. If it is artificial, what does that mean? Not just scientifically, but strategically, politically, existentially. Because if 3i Atlas is a probe from another civilization, we're not alone, and not being alone changes everything. Part 10, if it is artificial, ramifications. Let's assume, just for the length of this section, that 3i Atlas is artificial, a probe, a spacecraft built by intelligences that are not human, launched from a star system that is not ours, sent here for purposes we can only guess at. What does that mean for us? The best-case scenario is that it's a reconnaissance mission, a robotic explorer, fully autonomous, conducting a survey of the solar system. It's collecting data, mapping the planets, measuring the sun's output, sampling the composition of asteroids and comets, checking for biosignatures on Earth, Mars, maybe Europa or Enceladus. It's doing science. The same kind of science we're trying to do with our missions to other worlds. In this scenario, the probe is passive. It observes but doesn't interact. It's not here to make contact. It's here to gather information and report back, or maybe to add our system to a growing database of surveyed stars. This is the optimistic read. First contact is a mutual curiosity, civilizations exploring the galaxy, and eventually finding each other because we're all curious about what's out there. In this scenario, the solar Oberth maneuver makes sense as a mission design choice. You enter the system on a hyperbolic trajectory, pass close to the inner planets to maximize observation time, then use the sun's gravity well to accelerate back out. Maybe you're heading to the next star on a list. Maybe you're returning to your origin with a memory bank full of data. Either way, you're using the most efficient propulsion strategy available to a spacecraft with finite fuel. You're being smart about it. Economical. That's what we would do. That's what any rational spacefaring civilization would do. The implications of this scenario are profound but not immediately threatening. It means interstellar travel is possible. It means someone achieved it before we did. It means the galaxy is not empty. There are others out there, building machines, exploring, learning. It means we're part of a larger community, even if we've never met. It changes the context of human existence. We're no longer unique. We're no longer alone. Our achievements, our struggles, our history, all of it happens in a universe where intelligence and technology are not singular to Earth. That's humbling. It's also exciting. It opens futures we've barely imagined. Trade, communication, shared knowledge, maybe even collaboration across the light years. The long conversation begins, but there are darker scenarios. Surveillance without benign intent, intelligence, surveillance, reconnaissance, military terminology. If 3i Atlas is an ISR platform, it's not here to say hello. It's here to assess, to measure our capabilities, our technology level, our resource extraction, our military assets, our vulnerabilities. This is the reconnaissance that precedes action, not the exploration that satisfies curiosity. In this scenario, the probe might be part of a larger network, one of many sent to systems throughout the galaxy to identify targets of interest. The data it collects could be used to decide whether our system is worth visiting in person, worth exploiting, worth avoiding, or worth neutralizing. The Dark Forest hypothesis, popularized by Liu Cixin's science fiction trilogy, suggests that the galaxy might be filled with civilizations that remain silent because revealing your presence is existentially dangerous. If resources are finite and civilizations compete, the safest strategy is to hide and to eliminate any rival before they become a threat. In this framework, a probe like 3i Atlas is a scout. It's mapping the forest, identifying locations of other civilizations, reporting back to a predator that stays hidden until it's ready to strike. This is the paranoid interpretation. It's game theoretic. It assumes hostile intent because cooperation is risky and aggression is rewarded. It's also deeply unsettling because it implies that being discovered is the worst thing that could happen to humanity. Then there's the infrastructure scenario. The probe isn't just observing, it's deploying, establishing a relay network for communication, dropping sensors into orbit around the Sun or the planets, seeding the system with surveillance equipment or even kinetic delivery platforms. Small, inert objects that can be activated later if needed. This is strategic positioning, setting up the board for future moves. In this scenario, the Oberth maneuver could be used to place secondary payloads into specific orbits. You do your burn at perihelion, but instead of leaving the system entirely, you shed velocity and insert into a parking orbit. Maybe a heliocentric orbit that keeps you far from Earth but gives you a long-term observation platform. Maybe a Trojan orbit at a Lagrange point where gravitational balance lets you loiter with minimal fuel cost. You're not leaving, you're staying, watching, waiting. The strategic logic of a solar Oberth maneuver is compelling for any of these scenarios. The Sun's gravity well is the biggest energy source in the neighbourhood. If you want to reach the inner planets quickly, you fall toward the Sun and use the acceleration to whip yourself into the right trajectory. If you want to reach the outer system, same strategy, different exit angle. If you want to break into orbit, you retrograde burn at perihelion. The efficiency gain is enormous compared to burning in deep space. Any civilization with an understanding of orbital mechanics would use this technique. The fact that 3i Atlas's trajectory brings it to the optimal location for such a maneuver is why the speculation won't die. Detectability going forward depends on what instruments are watching and where they're positioned. Ground-based telescopes will recover 3i Atlas in early November as it emerges from solar conjunction. Observers will measure its position and brightness. Spectroscopy will continue. If there's any anomaly in the trajectory, any sign of post-perihelion acceleration or deceleration, it will show up in the astrometry. But detecting a transient event, a short thruster burn during conjunction, is much harder. You'd need space-based observatories with the right geometry and the right sensitivity. JWST could do it if pointed correctly, but JWST's observing schedule is planned months in advance. You can't just commandeer it for a comet watch. Hubble has some flexibility but limited field of view. Planetary orbiters around Mars or in the inner system might catch something if they're looking at the right time, but that's luck, not design. Policy implications are murky. If evidence mounts that 3i Atlas is artificial, who leads the response? NASA is the obvious US candidate, but this isn't just an American issue. The European Space Agency, JAXA, the Russian Space Agency, the Chinese Space Agency, all of them have stakes in solar system exploration. The United Nations has a Committee on the Peaceful Uses of Outer Space, COPUOS, which handles international space policy. There's also the SETI protocols, a set of guidelines developed by the scientific community for how to respond if we detect extraterrestrial intelligence. Those protocols emphasize transparency, international coordination, and avoiding hasty reactions. But the protocols were written with radio signals in mind, not physical objects in our solar system. The situation is different. The timeline is compressed. There's no time for leisurely international summits. Decisions would have to be made quickly, and the risk of unilateral action, one nation deciding to do something without consulting others, is real. Public communication becomes critical. The history of ambiguous, astronomical events shows that information vacuums fill with speculation and fear. The WOW signal in 1977 was a strong narrowband radio signal detected by the Big Ear telescope. It lasted 72 seconds and was never seen again. To this day, nobody knows what it was. In the absence of a clear explanation, theories multiplied. Aliens, Soviet satellites, comets, interstellar scintillation, terrestrial interference. The lack of follow-up data left the question open, and the ambiguity fueled decades of debate. If 3i Atlas remains ambiguous, if the post-perihelion data is inconclusive, the same thing will happen. Stories will circulate, theories will harden into beliefs. The truth, whatever it is, will be obscured by noise. Technological signatures to watch for include narrowband radio emissions. If 3i Atlas is transmitting data back to its origin, or if it's communicating with other probes in the system, it might use radio frequencies. Those transmissions could be detectable with Earth-based radio telescopes if someone's looking. Non-thermal infrared emissions are another signature. Spacecraft generate heat. Propulsion systems, power systems, even electronics produce waste heat that has to be radiated away. If 3i Atlas is active, it should glow in the infrared at wavelengths that don't match solar heating alone. Specular flashes are a third signature. If the object has reflective surfaces, solar panels, mirrors, or polished metal, those surfaces can produce bright glints when they catch sunlight at the right angle. If those glints repeat with a period tied to the object's rotation, that's evidence of artificial structures. All of these signatures are testable. They require the right instruments and the right observation plans, but they're within reach. Civilization implications are existential. If we're not the only engineers in the galaxy, our place in the cosmic hierarchy shifts. We're no longer the pinnacle of intelligence. We're one among many, possibly one among millions. That changes how we think about our future. It changes how we prioritize resources. If interstellar travel is real, if it's achievable, then our long-term survival might depend on achieving it ourselves. Staying confined to one planet in one solar system becomes a vulnerability. Expansion becomes not just an aspiration but a necessity. The Great Filter, the hypothetical barrier that prevents civilizations from becoming galaxy-spanning, might be behind us, or it might still be ahead. If 3i Atlas is proof that someone made it through, that's evidence the filter is passable. If it's evidence that someone made it through and is now scouting for resources or threats, that's evidence the filter is still operating, just in a different form. But let's be clear about one thing: zero impact risk. NASA's trajectory data is solid. 3i Atlas is not going to hit Earth. It's not going to pass dangerously close. The word trouble in this video's title refers to paradigm trouble, not kinetic trouble. If 3i Atlas is artificial, the trouble we're in is the trouble of having to rewrite our understanding of our place in the universe. It's the trouble of recognizing that the cosmos is more populated, more complex, and more dangerous than we thought. It's intellectual trouble, strategic trouble, philosophical trouble, not physical danger, at least not yet, not from this object. The trajectory is clear. It's leaving, or it's staying in a distant orbit. Either way, it's not coming for us. The final act of this story is about context, about the other things happening in science and space that change the background against which we interpret 3i Atlas. Fusion energy breakthroughs that hint at the power systems advanced civilizations might use. Cosmology discoveries that reshape our understanding of the universe's structure and history. Survey telescopes that will catch the next interstellar visitor earlier, with better data, giving us a chance to avoid the ambiguity we're dealing with now. These stories matter because they set the stage for what comes next. Part 11. Fusion. MassU uses 3D coils to tame ELMs. On a different front entirely, something remarkable happened in fusion research. The UK Atomic Energy Authority announced a world-first achievement at the MAST Upgrade Tokamak facility. They successfully controlled edge-localized modes using three-dimensional magnetic coils in a spherical tokamak geometry. If you're not steeped in fusion jargon, let me translate. They figured out how to stop a plasma instability that has been one of the biggest obstacles to practical fusion power. Fusion is the process that powers stars. You take light atomic nuclei, usually isotopes of hydrogen, and you slam them together at such high speeds and temperatures that they overcome their electrostatic repulsion and fuse into heavier nuclei. The process releases energy, a lot of energy. The Sun does this continuously, fusing hydrogen into helium in its core. If we can replicate that process on Earth in a controlled way, we have access to nearly limitless clean energy. No carbon emissions, no long-lived radioactive waste, just deuterium and tritium, both isotopes of hydrogen, fusing to produce helium and neutrons. The neutrons carry kinetic energy, which we capture as heat, which we use to generate electricity. The problem is containment. To get nuclei to fuse, you have to heat them to tens of millions of degrees. At those temperatures, matter becomes plasma, a fourth state where electrons are stripped from atoms and everything is ionized. Plasma doesn't touch walls. It melts anything it contacts, so you have to contain it with magnetic fields, shaping the plasma into a donut and holding it in midair with precisely controlled magnets. This is what a tokamak does. It's a magnetic bottle for plasma. But plasmas are unstable. They twist. They buckle. They develop instabilities that grow and crash, dumping energy into the walls and potentially damaging the reactor. One of the worst instabilities is the edge-localized mode, or ELM. ELMs are periodic bursts of energy that erupt from the edge of the plasma and strike the inner walls of the tokamak. Each burst is brief, but the cumulative damage over time can destroy the wall materials. This is a showstopper for commercial fusion. You can't build a reactor that tears itself apart after a few weeks of operation. You need to suppress ELMs, or at least mitigate their effects. Mast Upgrade did it. They used a set of three-dimensional coils, electromagnets arranged around the tokamak that create complex magnetic field patterns. These patterns disturb the plasma edge in a controlled way, preventing the conditions that lead to ELMs. It's like adding ripples to a pond to prevent larger waves from forming. The technique worked. The ELMs were suppressed, the plasma stayed stable. This is the first time it's been achieved in a spherical tokamak, which is a compact, efficient geometry that's central to the UK's plans for a commercial fusion power plant called STEP. Why does this matter for our story? Because fusion is the kind of energy source an advanced spacefaring civilization would use. Chemical rockets are limited by the energy density of their fuel. Even nuclear fission has limits. But fusion, if you can master it, gives you access to energy densities that make interstellar travel plausible. A fusion-powered spacecraft could accelerate continuously, building up to a significant fraction of light speed over the course of years. It could generate the electricity needed to run life support systems, communications, sensors, and propulsion all from a compact self-contained power plant. If 3i Atlas is a fusion-powered probe, the thermal signatures and the energy budget would be consistent with what Mast Upgrade and similar experiments are demonstrating on Earth. We're proving the physics works. Someone else might have already turned it into engineering. The Times covered the announcement, emphasising the significance for the UK's fusion programme. The official UKEA release goes into technical detail. The achievement is real. It's peer-reviewed in the sense that the results will be published in physics journals. It's reproducible. It's a building block for the next generation of fusion reactors. STEP is planned for the 2030s and 2040s. It won't produce power tomorrow, but the trajectory is clear. Fusion is no longer a distant dream. It's an engineering challenge being systematically solved. Taming star stuff in a bottle. That's what fusion is. Capturing the process that makes stars shine and putting it in a machine small enough to fit in a building. The magnetic braids, the three-dimensional coils, are like invisible hands shaping the plasma, keeping it from touching the walls, guiding it into stability. It's beautiful physics and brutal engineering. The temperatures, the magnetic fields, the precision required, all of it is at the edge of what humanity can currently achieve, and we're achieving it, which means someone else, somewhere else, with more time and more resources, might have achieved it long ago. Next, we need to talk about the universe itself, about dark energy, the mysterious force that's accelerating the expansion of space. Because new models suggest that dark energy might not have been constant throughout cosmic history. It might have spiked in the very early universe, changing the structure formation, and, indirectly, affecting the distribution of matter that eventually became stars and planets, and, perhaps, the civilizations that build probes like 3i Atlas. Part 12. Very Early Dark Energy Update. Cosmology is the study of the universe at the larger scales, how it began, how it evolved, where it's going. One of the biggest mysteries in cosmology is dark energy. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Galaxies are moving apart faster now than they were in the past. This shouldn't happen if gravity is the only force at play. Gravity pulls things together. It should slow the expansion. But instead, the expansion is speeding up. Something is pushing space apart, and we call that something dark energy. The leading model for dark energy is the cosmological constant, a term Einstein added to his equations of general relativity, and later called his greatest blunder. The cosmological constant represents a constant energy density filling all of space. It doesn't change over time. It doesn't dilute as the universe expands. It's just there, everywhere, always pushing space apart. This model fits most of the data, but it leaves questions unanswered. Why does the cosmological constant have the value it does? Why is it so small compared to what quantum field theory predicts? These are the cosmological constant problems, and they're unsolved. Recently, researchers at the University of North Carolina, including Alex Sobotka, have been exploring an alternative: very early dark energy, or VEDE. The idea is that dark energy wasn't constant throughout cosmic history. Instead, it spiked in the first few weeks after the Big Bang, then diluted away as the universe expanded. During that brief period, the extra energy density affected how matter clumped together. It changed the growth rate of density fluctuations, the seeds that eventually became galaxies and clusters. After the spike ended, the universe continued evolving, but the imprint of that early dark energy remained in the distribution of matter. Sobotka's modelling shows that V doesn't solve the Hubble tension outright. The Hubble tension is the discrepancy between measurements of the universe's expansion rate made using different methods. Observations of the early universe, the cosmic, microwave background, give one answer. Observations of the late universe using supernovae and Cepheid variables give a different answer. The two don't match. Something is wrong, either with our measurements or with our model of cosmology. VED tweaks the model, but it doesn't fully resolve the tension. What it does affect is small-scale structure formation, the way matter clumps on scales smaller than galaxy clusters. This has implications for the abundance and distribution of galaxies, which indirectly affects the rate at which planetary systems form, which affects the rate at which intelligent life might emerge. If VEDE is real, it means the universe had a different expansion history in its first moments. That changes the timeline for when the first stars formed, when the first heavy elements were synthesized, when the first planets could have habitable conditions. It shifts the window for life to appear. If advanced civilizations emerged earlier than we thought, if the universe was conducive to life sooner, that increases the probability that someone else is out there, older than us, more advanced, possibly exploring the galaxy while we're still figuring out fire. This is relevant to 3I Atlas because the context of our discovery matters. If interstellar visitors are common, if the galaxy is teeming with probes sent by civilizations that arose billions of years ago, then 3I Atlas is just one of many. If, on the other hand, intelligent life is rare and we're among the first, then 3I Atlas is an extraordinary anomaly. YVED doesn't answer that question directly, but it influences the background probabilities. The modelling is complex. It involves solving equations that describe how density fluctuations evolve in an expanding universe with time-varying dark energy. You have to match predictions to multiple datasets. The cosmic microwave background, large-scale structure surveys, gravitational lensing. Each dataset constrains the model differently. VEDA passes some tests but needs confirmation across others. New surveys like Euclid and the Rubin Observatory will provide higher precision data on small-scale structure, and that data will either support VED or rule it out. For the general audience, the takeaway is this: the universe might have behaved differently in its earliest moments than we currently think. That changes the conditions under which galaxies and stars and planets formed. It affects the timeline for life, and it reminds us that cosmology, the study of the universe's history and fate, is still an evolving science. We don't have all the answers. We're refining the model as new data comes in. And every refinement changes the context for questions like, are we alone? And how common are interstellar visitors? Part 13, Hubble Tension, Mirror Star Distance Ladder to 3.7%. Astronomers at the Inter-University Center for Astronomy and Astrophysics have pushed precision in measuring the universe's expansion rate to 3.7% using mirror variable stars as distance indicators. Mirrors are pulsating red giants with predictable brightness variations that serve as cosmic yardsticks, independent of the Cepheid variable and supernova methods that have dominated distance measurements for decades. This matters because when different measurement techniques agree, it suggests systematic errors are less likely, and the Hubble tension, the maddening discrepancy between early universe and late universe expansion rate measurements, might point to genuinely new physics rather than observational mistakes. Better cosmic distances mean better understanding of how matter distributes across space, which affects our estimates for how many planetary systems exist, which affects how we calculate the probability of other technological civilizations arising. If 3I Atlas is artificial, these calculations shift from theoretical exercises to urgent strategic assessments. The Mirror study, co-authored with members of Adam Rees's team who've been leading the precision cosmology charge, adds another independent check to the cosmic distance ladder. It doesn't solve everything, but it tightens the constraints, and tighter constraints mean we're closer to understanding whether the universe's structure favours rare or common technological life. Part 14. Surveys that change the game. Euclid plus Rubin. The European Space Agency's Euclid mission has begun delivering science data, demonstrating exquisite wide-field imaging and spectroscopy that can probe low surface brightness features and map cosmic structure at unprecedented scales. Meanwhile, the Vera C. Rubin Observatory has delivered its first light images, each frame capturing an area equivalent to 45 full moons, with a camera so sensitive it could detect a candle flame on the moon. Rubin's legacy, survey of space and time, will scan the entire visible sky every few nights for 10 years, and astronomers estimate it could detect between 0.9 and 1.9 interstellar objects per year. That's dozens over the mission lifetime, caught earlier in their approach with far better tracking than the rushed observations of 1I/Oumuamua, 2I/Borisov, and 3I Atlas. Earlier detection means longer baseline observations before perihelion, which means better chances to flag non-gravitational behaviour before objects enter solar conjunction blackout windows. Automated machine learning pipelines will scan Rubin's data stream for anomalies, flagging anything that moves strangely or looks morphologically unusual. When the next interstellar visitor arrives, we won't be caught flat-footed. We'll have months of pre-perihelion data, multiple independent observatories confirming morphology and chemistry, and time to coordinate international observation campaigns. The leaked images and ambiguous data surrounding 3I Atlas might become historical curiosities, artifacts of a time when our detection infrastructure wasn't ready for what the galaxy was sending us. Or they might be the first chapter in a longer story, one where we realise the visitors have always been here, passing through, and we've only just started to notice. Part 15. What to watch next. In early November 2025, 3I Atlas will emerge from solar conjunction. Observers worldwide will point their telescopes at the predicted coordinates and measure where the object actually is. They'll compare the observed position to gravity-only predictions and calculate residuals. If those residuals are consistent with random cometary outgassing, the craft hypothesis weakens significantly. If they show systematic deviation, a velocity change pointing in a specific direction, with magnitude larger than outgassing can explain, the conversation shifts immediately. Spectroscopy will continue. JWST, Hubble, Keck, and VLT will capture chemical profiles, searching for emissions that don't fit natural models. Amateur astronomers like Tiago will continue solar telescope monitoring through November, documenting morphology changes and looking for the tail that should develop as the object moves away from perihelion. Space assets, including SOHO and Stereo, will process their conjunction period data, and those datasets, when released, might contain the only direct observations of 3I Atlas during its closest solar approach. We'll watch for radio emissions, infrared anomalies, and specular flashes that repeat with the object's rotation period. Every observation is a test. Every data point either supports or challenges the natural comet model. NASA states unequivocally that there is no impact risk. 3I Atlas will not hit Earth. The trouble implied in this video's title is paradigm trouble, the trouble of confronting evidence that challenges our cosmic solitude. If the post-perihelion data shows nothing unusual, if 3I Atlas behaves exactly as a comet should, we'll add it to the catalogue as a fascinating but natural interstellar visitor with unusual chemistry. If the data shows anomalies that can't be reconciled with natural processes, if the trajectory deviates, or the morphology resolves into obvious artificial structures, humanity faces a decision point. Do we attempt communication? Do we passive monitor and gather more data? Do we convene international bodies to coordinate policy? The SETI protocols exist, but they weren't written for physical objects already in our solar system on trajectories we can predict. We're in uncharted territory, flying blind through the conjunction window, waiting for the sun to move aside so we can see what happened while we weren't looking. This might be the moment when everything changes, when we learn we're not alone and never were. Or it might be another strange comet, one more mystery in a universe full of them, reminding us that nature is stranger than we imagine and stranger than we can imagine. Either way, the data will come. The observers are ready, the telescopes are pointed, and in a few weeks we'll know more than we do right now. Until then, keep watching the sky. Because whatever 3I Atlas turns out to be, it won't be the last visitor. The galaxy is vast, the stars are many, and the space between them is no longer empty. We're listening now, we're watching, and eventually one way or another we'll get our answer.